Okay, here is your key for the AP style test. Let's see what we got here. At time t equals 0, so at time t equals 0, water begins pouring into an empty vase at a constant rate. A graph that's not shown models the depth of the water in the vase over time. The water pours into the container until it is full. Match the following vases to the given description of each graph. Okay, so graph 1. The graph is always increasing at a constant rate. So if it's always increasing at a constant rate, that would look like it would be linear. And if it's going to increase, remember what is increasing is the depth of the water. If the depth of the water is increasing at a constant rate, the vase would have to look like this. So this would be graph 1. Okay, so got that. Then it says the graph is always increasing. First half of the graph is concave up, and the second half is concave down. So let's talk about our fun chart here. Here's my fun chart. The rate. All right, so if the function is concave up, the rate is increasing. If the function is concave down, the rate is decreasing. Okay, so it says the graph is always increasing, which means water is always going in there. The first half is concave up, so if it's concave up, the rate is increasing. If the water is going in faster, then that means it's going to get deeper quicker. So it looks like this one would probably be, this would be going slowly, or it would be actually slowing down because my diameter, is getting bigger. Here it looks like we'd be speeding up. Okay, so I think I like that these two here, B and C, would be concave up at the beginning, but this is the first half. And then the second half is concave down, which means the rate is slowing. And so if it's getting, so here we go. We're filling it up. It's going to fill up quicker because it's getting skinnier, and then the rate is going to slow down. This would be graph 2. All right, so graph 3, again, always increasing. All of them are. The first half is concave down. The second half is concave up. So as the water fills in here, the rate at which the height is going to change is going to slow down because it's getting wider. And then the rate at which the depth changes is going to speed up. So that would mean concave down and then concave up from our fun chart. So this would be graph 3, which of course leaves this for graph 4, but let's make sure that this makes sense. Always increasing. Okay, there are 4 portions to the graph. The first portion is concave up, then concave down, then concave up, then concave down. So that would mean the rate is increasing, then decreasing, then increasing, then decreasing. So look at this. Remember, it's the rate at which the depth of the water changes. So the depth of the water, the rate at which it changes is going to increase and then decrease and then increase and then decrease. So this is graph 4. All right. So here it says the figure shows the graph of function g for x being between -4 and 4. The endpoints of the interval are labeled with A and G. The 2 other extrema for G are labeled points B and D, or B, D, and F. Points C and E are the only points of inflection on the graph. And then we are going to let these right here represent the x coordinates, and then we have to write about the intervals of G where the rate of change is doing these things here. So if I'm talking about the rate of change, I want my fun chart. Okay, so if my rate of change is positive and increasing, so the rate of change is positive, oh goodness, the rate of change is positive and increasing, I am looking for the function to be concave up and increasing. All right, so concave up and increasing is right here and right here. Okay, so remember, these represent our x values. So I'm going from b, which is t sub b, to c, which is t sub c. And then I'm also going to use t sub f to t sub g. Okay. Then I want my rate of change to be positive and decreasing. If the rate of change is positive and decreasing, the function is concave down and increasing. So it's only concave down from C to E, but concave down and increasing would be here from C to D. So this would be T sub C to T sub D. All right, so then I need my rate of change. Sorry, I keep getting my eraser. My rate of change to be negative and increasing. If my rate of change is negative and increasing, I need my function to be concave up and decreasing. So concave up and decreasing would be here and here. So that means I'm going from T sub A to T sub B, and then T sub E to T sub F. Okay. Then negative and decreasing would be concave down and decreasing, and so that would be here, T sub D to T sub E. And remember, with positive and with concave up, concave down, any of these intervals, we want open parentheses. Okay, next part. I'm going to determine if the functions could be concave up, concave down, or neither. This is not where I'm looking for the first, second, third differences. Okay, that determines degree. Concave up and concave down is determined by my fun chart. If I don't have a graph. So concave up and concave down would mean I'm looking for the rate of change to see if it's increasing or decreasing. So the first thing I'm going to look at is if I have equal length intervals. So these are all 3. That's good. Okay. So I can find my rate of change here. So -3 minus a -10 is a +7. So 7 over 3 is my rate of change. 2 minus a -3 is 5. So I get 5 over 3. 4 minus 2 is 2 over 3. And then 5 minus 4 is 1. So I get 1 over 3. All right, so let's look at what we have and let's think about this for a second. Because these are equal length input intervals, and nobody asked me for what the actual rate of change is, even if I only found the first differences here and I got a 7, a 5, a 2, and a 1, that would still be enough to tell me what's happening because they're all going to be divided by the same number. So it is okay to kind of take that shortcut, but you have to know the difference between whether you're really talking about the differences or talking about the rate of change. Because I can talk about what the rate of what's happening with the rate of change even if I don't find it. But what I looked at here, this is not constant, and that's fine. I'm looking at the fact that my rates of change are decreasing. And if my rate of change is decreasing, then my function is concave down. So I could say f could be concave down because average rates of change are decreasing, oh, average rates of change, dang it, sorry. Okay, erase, thank you. Average rate of change, we have to be specific here, of F are decreasing over equal length inputs. It's really equal length input intervals, but I'll let that slide. Okay, so let's look at this one. I'm going to look at my differences here to make sure I have equal length inputs, and I do. Okay, so I know all the differences I find here will all be divided by 10, but I don't have to even just divide it by 10 because I just want to see if it's increasing or decreasing. So -2 minus 0 is -2. -4 minus a -2 is a -2. -8 minus 4 is -4. And -16 minus a -8 is -8. So remember, these numbers here are not the actual rates of change. However, whatever's happening with these numbers is what would be happening with my rate of change. So even though these are decreasing, from here to here, it's the same. So it's not decreasing the whole time or increasing the whole time. So yeah, part of it would be concave down, but not all of it. And right now we're talking as the whole thing. So we can say that G could not be strictly concave up or down because average rates of change of G are constant, then decreasing, something like that. Okay. All right, C. I'm going to look for these differences here. So it's 1, 1, 1, 1. So my differences here actually will be my rates of change because I'm dividing by 1. So 32 minus 64 is a -32. 16 minus 32 is a -16. 8 minus 16 is a -8. 4 minus 8 is a -4. All right, so when I look at this, my rates of change are increasing. So I could say that H could be concave up because average rates of change of H are increasing over equal length inputs. All right, there you go, concave up and down. All right, so now we have, the figure above shows the graph of f of x. Determine the key features at each labeled point using the word bank below. If the point is a 0, determine the multiplicity, and these are the only 3 things I could use. Some points could have more than one key feature, and then here's our word bank. All right, so we're going to start with A. A is a relative maximum, so this is a relative max. It is also a 0, and since it bounces off, it is tangent to the axis, that means that we have to have an even multiplicity. Okay, just by looking at the graph, we don't know what that multiplicity is. But if my only choices are 1, 2, or 3, then my multiplicity would have to be 2. All right, so then B. Here's point B. All right, well, it's not a maximum or a minimum. It's not a zero, so my option 0, point of inflection sounds right, but it's not an absolute max or min. So this is where the concavity changes from concave down to concave up. So this is a point of inflection. All right, C. Here is point C. Not a zero, not a point of inflection, but it is a relative max or min. So that would be a relative minimum. Now let's talk about why it's not the absolute minimum. It's not the absolute minimum, even though it is lower than this one, because this goes down to negative infinity, so I don't have an absolute minimum. And A is not an absolute maximum because it's not the largest y value that we would have there. Okay, so then next we go to D. D is right here. D is not a zero or a max or min, but it is where we change from concave up to concave down. So D is a point of inflection. All right, so then we have E. E is a zero. It's not a max or min or anything else. It's just a zero. But remember, we have to look at multiplicity here. And this is just a boring old pass through the axis. So it's just a zero, which we really don't label multiplicity of 1, but I think this kind of says 2. So we'll put multiplicity 1 there. All right, next is F. Here is F. It is, again, not a zero, clearly not a point of inflection. It is a relative maximum, but still not the biggest one, so it's not the absolute, but it is a relative maximum. I guess here, since I had room, I really should have written out the whole word. Didn't really have room on A. Okay. Then G. All right, so G is not a max or min. It is going to be a point of inflection. It's where we change from concave down to concave up. So point of inflection. All right. Then H, right here. So that is not a relative max or min. It is a zero. So let's say that it's a zero. Let's talk about that first. Multiplicity. Okay, so this is one thing that I didn't really stress because I don't think it's really like going to be on the AP test, but I do think it's good to know. If we have an even, and I know we talked about it, but we have an even multiplicity, then we have a balance that's tangent to the axis. If there's no multiplicity, it's just a boring old pass through. If I have a point of inflection at the zero, which that's what this is, we'll go back and talk about that in just a second, then I have an odd multiplicity greater than 1. And since these are my only choices, we would have a multiplicity of 3. Okay. And again, this is a point of inflection. I am changing from, it is concave up right here, and then it changes to concave down. And a point of inflection is where you change your concavity. So this is a point of inflection. All right. Then J, we've got, here's J. Again, not a max or min, not a zero, but this is concave down, then it changes to concave up. So this is also a point of inflection. Then K is right here. That is a relative minimum. L right here. That is a 0. And again, it's just a boring old pass-through, so it doesn't have a multiplicity, but since 1 is listed there, we will put that it is a multiplicity of 1. It is not a point of inflection because this is remaining concave up. There wasn't a change in concavity there. And then we get to M, and at M, here's this point here. That is a relative minimum. Because all maximin are relative maximin, but then it also fits in the category of absolute minimum. Okay, and there's page 2. Alrighty, so we're going to match each polynomial function to the correct graph. All right, so let me show you how I go about this because there's all this stuff going on. I'm going to look at what my zeros are here and what I have. So this I know is it's a bounce, so I would have an even multiplicity. All of my answers up there, they're just squared. So this would be x minus 2 squared. This, since that's at -2, this would be x plus 2 squared. This would be x minus 2 squared, and this would be x plus 2 squared. Okay, so that narrows it down, but then I have to decide also on my leading coefficient. So since this is up, I know that if the right-hand side is up, then this has a positive leading coefficient. Right-hand side is down, it's a negative leading coefficient. Right side down, negative leading coefficient. Right side up, positive leading coefficient. So I'm looking for a positive leading coefficient with an x minus 2 squared. So here's x minus 2 squared, positive leading coefficient. This is A. Then I have x plus 2 squared, negative leading coefficient. That is this, so this would be B. X minus 2 squared with a negative leading coefficient. That would be this one right here, which is C. Oh, goodness, sorry about that. And then this would be x plus 2 squared with a positive leading coefficient, so this would be D. Okay, so that's one way to kind of look at all that. Plus, there wasn't like a whole lot of stuff to choose from here, but clearly I have a 0 at 0, and that is true for all of these, And then I would have a 0 at a positive 3 here. You can double check that, and a 0 at -3 there. Okay. So this says complete the left side of each graph to make the symmetry true. I'm going to make f of x even on this interval. And so if it is even, here's some things we need to know. We seem to really struggle with that. If it's even, f of negative x equals f of x. That means if I have an ordered pair xy, there is also an ordered pair negative xy. And if it is even, it has y-axis symmetry. Okay, so that means, so 0, 0 would be 0, 0. This point that's 1, 1, I'd have a negative 1, 1. Basically, everything just reflects across the y-axis. So this point, which is at 2, 3, I'd have a point at negative 2, 3. This point here, which is at 3, 1, I'd have it negative 3, 1. This point here, which is at 4, negative 2, I'm going to go to negative 4, negative 2. And then 5, negative 4 would be at negative 5, negative 4. Okay, so I got all those points on there. And remember that this is not an art class, but we want to attempt to, try and draw something that's semi-decent looking. Okay, and then this is gonna, something kind of like that. That's good enough. It's terrible, but it's good enough. All right, so then if it's odd, if the function is odd, f of negative x equals negative f of x, which means if I have an ordered pair xy, I have another ordered pair negative x, negative y. I change the sign on both, and this has origin symmetry. So 0, 0 is 0, 0. This point that is at 1, 1 would end up at negative 1, negative 1. The point that's at 2, 3 would end up at negative 2, negative 3. The point at 3, 1 would end up at negative 3, negative 1. The point at 4, negative 2 would end up at negative 4, 2. And the point at 5, negative 4 would end up at negative 5, positive 4. Okay. And remember, when you turn this upside down, you want it to look the same. That's what would happen here. And so this would look something like this. And I would have this. And this would swing in and then out, kind of like that. Again, make an effort, you'll be fine. All right, so here we want to describe the end behavior of each of the following using limit statements. Okay, so I'm going to look for the leading term, which would be this. That is a positive leading coefficient, so the right side goes up. Then it's even, the degree is even. It is not necessarily an even function, but the degree is even, so the left side is the same. Okay, now be careful with your limit notation when you're writing. The limit as x approaches negative infinity, because it is telling me end behavior. And then of f of x is equal to, so when x is approaching negative infinity, f of x is approaching infinity. Then the limit as x approaches infinity of f of x is also infinity. All right, so then here on C, well, I'll do C next. I'm looking for my leading term, which is right here. That leading coefficient is negative, so the right side goes down. The degree of the function is even, so the other side is the same. So the limit as x approaches negative infinity, notice how those are stacked, of h of x, don't call everything f, that is equal to, since this is pointing down, negative infinity. Then the limit as x approaches infinity of h of x, that's equal to negative infinity. All right, on B, looking for my leading term, that would be this one. It is positive, so the right side goes up. The degree is odd, so the left side is opposite. So my limit as x approaches negative infinity of g of x is equal to negative infinity. And the limit as x approaches infinity of g of x is equal to infinity. All right, here looking for my leading term, this would be it. So leading coefficient is negative, so this side is down. The degree is odd, so the left side is opposite. So the limit as x approaches negative infinity of k of x is equal to infinity. And the limit as x approaches infinity of k of x is equal to negative infinity. And there's page 3. All right, page 4. For the love of all that is holy, I swear on the Holy Maverick that if y'all cannot find the average rate of change, which is just slope, I think my head might explode. So, and use your function notation. given f of x, here's my function, determine the average rate of change. That just means slope, old slope that you learned before you did Algebra 1 and that you have done every single year since. And we're finding it on this interval. So here's my function notation since I'm on this interval. It is f of 2 minus f of negative 9 over 2 minus a negative 9. Now, I need to find f of 2 and f of negative 9. So, I'm going to find f of 2. That's going to be negative 2 squared minus 9 times 2 plus 26. So, that is negative 4 minus 18 plus 26. So negative 4 minus 18 is a negative 22 plus 26 tells me f of 2 equals 4. Then I'm going to find f of negative 9. So I have negative 9 squared minus 9 times a negative 9 plus 26. Okay, negative 9 squared is a positive 81, but then there's a negative out here, so I have a negative 81. Then negative 9 times negative 9 is a positive 81, and then I add 26. These zero out, so f of negative 9 is 26. You can't even get to where you can do slope if you don't know what to do with positive and negative integers and how to evaluate a function. All right, so back over here. Now I'm going to substitute this in. F of 2 is 4 minus f of negative 9, which is 26. And then 2 minus a negative 9 is 11. 4 minus 26 is a negative 22 over 11, which gives me in the end a negative 2. And that is my answer. And that is basic slope. All right. Determine which of the following functions have an absolute maximum, absolute minimum, both, or neither. All right, so here again, we're basically just trying to figure out what the end behavior is. And so I look at my leading term. This is an odd degreed function. It's not an odd function, it is an odd degree function. The leading coefficient is negative, so the right-hand side goes down. It's an odd degree, so this is opposite. If I have an odd degreed function, I'm not going to have an absolute maximum or minimum. So I can say f has neither because f is an odd, I can't say an odd function, an odd degree function. All right, so on B, here's my leading term. The leading coefficient is positive, so the right side goes up. The degree is even, so the left side is the same. So since it goes up, up, that means that leaves something down here for an absolute minimum. So I can say G has an absolute minimum because G is an even degree function with a positive leading coefficient. Okay, you got to say something about the degree and the coefficient. All right, here, this is my leading term. Leading coefficient is positive, and then the degree is odd, so it's opposite. So when you have an odd, so really the positive and negative doesn't even really matter here because you have an odd degree function, you're not going to have either one. So F has neither because f is an odd degree function. All right, h. Here is my leading term. Leading coefficient is negative, so right-hand side points down. The degree is even, so the left-hand side is the same. So that means I'm going to have an absolute max. So I say h has an absolute max, maximum, because h is an even degree function with a negative leading coefficient. Period. Okay. Find all zeros, real and complex, for the following functions. That means you got to solve them. That means you get an output of 0 and you set it equal to 0 and you factor. So 0 equals, and I'm going to factor out this negative 5. Negative 5 times x squared minus 16, which means I can factor and get negative 5 times x plus 4 times x minus 4. That negative 5, this does not give me a 0 because there is no variable on it. Now, I can't completely drop it off, or I don't have equality going on, but he does not affect my zeros at all. These are the only two. I only have 2 x's in there. I can only have 2 zeros. This is an x squared. At most, I can have 2 zeros, real, imaginary, whatever. So here, when I solve that, I get x equals plus or minus 4. All right, got to set it equal to 0. I'm going to go ahead and factor out that x. That leaves me with 5x squared plus 4x minus 9. Unfortunately, I couldn't factor out that 5, so I have an a that is not 1, so I'm going to factor by grouping. 5 times negative 9 is a negative 45. All right, so 0 equals, I cannot drop this guy off. He is very important, but I'm going to split that middle term. So I need 2 numbers that multiply to give me 45, and negative 45, and combine to give me 4. So that would be a positive 9 and a negative 5. If you don't know your multiplication facts, that makes that a lot harder for you. Plus 9x minus 5x minus 9. All right, so then since I'm going to factor by grouping and have to use a bunch of parentheses, I'm going to throw in some brackets here because I like that better. Do that. Out of these 2 terms, I can factor out an x. That leaves me with 5x plus 9. Out of these 2, I can factor out a negative 5. That leaves me with, oh, not a negative 5. I'm sorry. That makes no sense. I'm going to factor out a negative. That leaves me with 5x plus 9. All right, so it's really a negative 1 there. And then I can drop my brackets, x, so then I get x minus 1 times 5x plus 9. Now, what I've seen a lot and what hurts you on some number lines and other things when you had to factor is y'all losing this guy. Either losing this guy or making stuff up with this one. Like, I don't know. Some of y'all, I'm not sure. I don't know if it's the same people doing the same thing, but I end up, this was an x cubed. I should have 3 zeros in the end. Then I have, you know, with my, unless I have multiplicity, and they could be imaginary, but I have 3 things here. I need to have 3 zeros. So my zeros in the end would be negative 9/5, 0, and 1. All right, so let's look at C. All right, now I have a GCF, so I'm going to factor out that GCF, and I would like to factor out that negative. So 0 equals negative 2 times x cubed minus x squared plus 4x minus 4. Okay, that's how that works. Then I'm going to, this is factoring by grouping, but I don't have to split the term because I already have 4 terms there, so that's nice. So I'm going to throw in my brackets again. Out of those two, I can factor out an x squared. That leaves me with x minus 1. Out of these two, I can factor out a 4. That leaves me with an x minus 1. Then the next step, I can drop my brackets. I get x squared plus 4 times x minus 1. All right, so I cannot factor this anymore. I need to come up with my zeros here. This does not give me a 0. This does not give me plus or minus 2. If you need to write it out, this is x squared plus 4 equals 0. So x squared would equal negative 4. So x equals plus or minus the square root of negative 4, which is plus or minus 2i. So plus or minus 2i, and then this gives me a 0 of 1. And those are my zeros right there. Okay, so now I need to do a number line. And sorry, I'm trying to make this where I can make it fit. All right. Because I want to find the intervals for where the function is positive and negative, and I don't have a graph to look at. So I need my number line. They were nice enough to factor this for me. But if you have one that's not factored, you have to factor it accurately, or you don't have any of the right numbers on your number line. All right, so I have 3 zeros here. So let me just write them out. I've got 0, negative 7, and 4. So I'm going to put those 3 on here. Negative 7 has to come first, then 0, then 4. All right. And then I can't really put an open or close on here yet because I'm asked multiple questions, which is fine. So let's just figure out our signs first. If I have 3 terms with x, I'm going to have 3 positive or negative signs for each one. You got to use them all. So here I'll pick like a negative 8. Negative 8 squared is a positive 8. So since this is squared, anything I substitute in is positive. First thing's positive no matter what. Negative 8 plus 7 is negative. Negative 8 minus 4 is negative. So that makes this positive overall. Between negative 7 and 0, I could do a negative 1. Well, I know the first thing here is going to be positive no matter what. Negative 1 plus 7 is positive. Negative 1 minus 4 is negative. This is negative overall. Then between 0 and 4, I could pick 1. So this first one's positive no matter what. 1 plus 7 is positive. 1 minus 4 is negative. That makes this negative overall. Then I could choose 5. First thing's positive. 5 plus 7 is positive. 5 minus 4 is positive. So this is positive overall. Okay, so let's see what we're looking for here. We are looking for the function to be greater than 0, so that means I want it everywhere where it is positive. And I cannot include 0, so basically I just pretend like I have open circles. So the positives are here and here. So I'm going to go from negative infinity to negative 7, and I'm not including it because there's no line underneath there. And then I'm also going from 4 to infinity. Okay. All right, so then I want when f of x is greater than or equal to 0, so that's when it's positive and 0. All right, well, it is positive from negative infinity to negative 7. I never include my infinities, but at negative 7, it is 0, so I do include that guy. Then this is where notation gets a little weird that I don't know that I really talked about in class. I think it was on a worksheet. And I don't know that you would be asked for this type of thing on the exam, but I guess it's possible. Because I have to include all 3 of these zeros, right? And here on either side of this, it's negative. I want it to be positive. Oh, positive and 0. What happened to my 0? So I need to include this guy. not because this number is 0, but because it's one of the 3 zeros. So to include that when you're doing interval notation, one way to do it looks like this, which might look kind of weird, but that's what happens. And then this is positive again here. And so I'm going from 4 to infinity. Never include my infinity, but I am including 4 because of this line down here. All right, f of x is less than 0. That means we want this to be negative. Here is where our negatives are. This is negative, and I can't go straight from -7 to 4 because I don't get to include my zeros here, so I have to jump over this guy. So I'm going to go from -7 to 0, and then and not include them, and then from 0 to 4. Okay. Then this means I want it to be negative, and I can include 0. So it starts being negative here at -7. Then it's negative, that's 0, and then it's negative until you get to 4. So you get to include, and we're including the zeros here, so I'm including -7, and I get to go straight from -7 to 4 because I get to include him. I didn't have to jump over him like I did here. Okay, so there's your review. Remember, reviews are not the end-all be-all. Look back over your notes, look back over your assignments, your quizzes, and definitely look back over your AP classroom questions. You can do well on this.